Hi.
Hello, Ramit.
Hi, yeah.
How are you?
I'm fine, thank you. How are you?
Okay. Am I clearly audible?
Yeah, everything is fine.
Okay, okay, okay. Let me introduce myself first. Okay. Myself,
Yeah,
myself Ritesh Misra, and
okay.
I have done my MTech in 2016 from Mechanical Thermal Engineering Department. Okay, and
Okay.
after that I have almost 7 years teaching experience. And presently I am an assistant professor in engineering college. Okay, and
Okay.
doing part time teaching for a gate exam in India. Gate exam uh, is the competitive exam for any job oriented. Okay,
Yep.
so okay, so I have seen all your PDF and tutorials, and
Sure.
through all the tutorials I have realized that the following syllabus you will have to covered. Okay,
Yeah.
first is introduction part. In introduction part, in this part, we basically learn about the system, surrounding, boundary, what is zeroth law. Okay, in,
Okay.
in the introduction part. And after that, in the energy interactions, in this section you will learn about heat and work.
Okay.
Heat and work. Okay, and after that, first law of thermodynamics, which is the conservation of energy. You know that.
Yep.
And after second law of thermodynamics, and application of thermodynamics is also there. This that is modes of heat transfer. In
Okay.
this section you basically learn about what is conduction, convection, radiation. These are the modes of heat transfer you will learn in this topic. And after that we will move to the entropy and exergy part.
Okay.
Exergy is basically you call it available energy. You will call it available energy. So we will learn available energy in this topic, exergy part. Okay,
Okay.
and at last, properties of pure substances, which is very important for your thermodynamics point of view. Here you will learn TS diagram of pure substance, PV diagram, what is PV diagram, HS diagram. Okay, different types of diagram you will have to learn in this topic, properties of pure substance. Okay,
Okay.
so these are the following topic you will have to cover for your exam and tutorials. And we will move slowly, and from the first part, as we complete this topic introduction, then I will solve the questions based on this topic as given in
Okay.
your tutorials. Okay,
Hmm.
and after that, every in every topic in every topic in every topic, the all questions which is asked in the tutorials, I will be solved in this in the session. Okay, and you will learn
Okay.
that problem easily. Okay,
Okay. Okay.
so let's start your thermodynamics. And today I will start introduction part. Okay, and
Okay.
I will move slowly so that you can easily understand each and every concept. Okay,
Okay.
so let's start. Okay, so I will start thermodynamics. What is thermodynamics? What is the application of this part? And after the session, I will share the PDF of this session to you. Okay, so
Okay.
that
Okay.
so that you can easily revise this. So dear, thermodynamics, as you see, thermodynamics is basically, it is made up of two Greek word. Okay. First word is,
Okay.
first word as you see is therm. First word is called therm. And second word is dynamics.
Thermodynamics, yeah.
Okay. These two words are Greek word. Okay. And this therm is called heat. This therm is called heat. Okay. And dynamics is basically motion. Anything which is in motion, anything which is in motion will be studied in dynamics part. Okay. As you have studied in engineering mechanics. Okay. Statics part, kinematics part, dynamics part. Okay. In dynamics part, body is in motion. Okay. So when body is in motion, that means body will have power.
Yeah.
When a body has power, then it will move. Okay. So motion, dynamics means power. And here power is what? Power is the rate of doing work. As you know that power is rate of doing work.
Yeah, rate of energy transfer. Yeah.
Okay. Okay. Yes, rate of doing work. That means power is nothing but work divided by time. So here we relate both the terms. Dynamics, in the dynamics part, work by time. Okay. And in the therm part is basically the heat. Okay. So thermodynamics is made up of two words. One is heat and other is work. As you see this work. Okay.
Yeah.
So thermodynamics is basically made up of two words, heat and work. Now understand what is heat and what is work. So heat and work both are basically the type of energy transfer. Both are the types of energy transfer. Okay. But heat is called disorganized form of energy. Disorganized form of energy. Why it is called disorganized? I will tell you. Okay. Disorganized form of energy. And work is called organized form of energy. Organized form of energy. Okay. Now see, here disorganized form of energy means you cannot completely convert heat into work, but we can easily convert work into heat fully. Okay. Heat cannot be converted fully into work, but work can be fully converted into heat. Okay. So that's why heat is called disorganized form of energy. Okay. And work is called organized form of energy because we can easily convert them into heat fully. So work is called organized form of energy. And from here, one more name is given to the work, that is high grade energy. High grade energy. High grade energy means it has more values as compared to the heat. It has more values because we use only work. As you see in the turbine, as you have learned about turbine. In the turbine, for example, this is your turbine. Okay. This turbine may be your water turbine, maybe a steam turbine, maybe gas turbine. Okay. So this is your turbine. In the turbine, in the turbine, work is done by this turbine, and this work, we easily convert this work into electric power. Okay, so we utilize work. We utilize work in our daily basis energy requirement, but we cannot completely convert heat into our utilized form. Okay, this work transfer that is given by the turbine to us is completely converted by us to the electrical energy. That means electric power. Okay. Okay. And one more example, as I have told you that work can be completely converted into heat.
Yeah.
Now I am giving you an example how work can be completely converted into heat, and when, in which device we have seen the work is completely converted into heat. So my dear, in a device, perhaps you have learned about that device, throttling device.
Throttling device. No, I've never heard.
Okay. I will teach you about throttling device. Okay, later in the thermodynamics part, throttling device, I will teach you. Okay, in the throttling device, this throttling device is basically just like your turbine. It is just like turbine. In turbine, there is the pressure reduction. In the turbine, there is the expansion process of substance, so we get the work. In throttling also, here it is also pressure, it is also the expansion device. Here also pressure reduces, so we will have a chance to get the work here, because in turbine pressure decreases, so we get the work. In throttling also pressure decreases, so we have a chance to get the work here. Okay, but the work obtained in the throttling device is fully lost. Okay, due to the high friction. This work is fully lost due to high friction, because throttling device is a restricted device. Here a small passage is given. In that small passage, the substance is flowing, so it is called restricted flow. And due to this restricted flow, high friction occurs, and the work which I have to obtain here is completely lost due to the friction. Lost. This work is lost due to friction. And now think, here work is completely lost due to friction. Then what happened? Then this work is completely converted to heat here. Due to friction, this whole work is converted into heat.
Okay.
So this is the practical example of how work can be completely converted into heat. Okay. Later I will discuss throttling device. Okay. Later I will discuss throttling device, and you will easily understand what is throttling. I will give you example and its numerical analysis. Okay.
Yeah.
Now how heat cannot be completely converted into work. Now the question arises, okay sir, you have told that work can be completely converted into heat. Okay, but how heat cannot be completely converted into work? Okay, let's see. Let's take an example of a heat engine. Let's take an example of heat engine. This is your heat engine. This heat engine is working between two temperature. This is T1 and this is your T2. Okay. These temperatures are reservoirs. Okay. In these two temperature limits, our heat engine is working. And in the heat engine, Q1 heat, assume that Q1 heat is absorbed by this engine from the T1 reservoir, and this heat engine will do some work, and remaining heat will be rejected, that is Q2. Remaining heat will be rejected, that is Q2. Here you can easily see that here heat is cannot completely converted into work, because here if we balance the energy, we can write that Q1 is equal to W plus Q2. W is work. So here you can see that heat is cannot converted into work completely. Some heat is also rejected. So we can say that here W is less than, work is less than Q1. We supply the energy, we supply this heat engine by energy Q1, and we want that this energy is completely completely converted into work. We want that Q1 is completely converted into work, but this does not happen in this device. Some heat also goes to the sink as waste. Okay. So heat cannot be completely converted into work. This is the technical example. I will give you a daily routine example. You will easily understand. Let us take a human body, our human body. Okay. This is our human body. Okay. Okay. We take heat as input from the food. From the food, we take energy to this body. Okay. So food is the form of heat energy, and you will tell this chemical energy. The chemical energy, form of energy is chemical. Okay. So we take the food, and from the food we get the heat energy. Okay. And as we know that some heat energy is wasted. Okay. Some heat is wasted. Some heat will go waste from our body. But some heat is stored in our body. Some heat is stored in our body. Let us take a value. If we take 100 joule of energy, in our body, and body reject 40 joule heat as waste, then our body will store 60 joule of energy. Body will store 60 joule of energy. This 60 joule of energy is utilized in two things. First thing is our internal energy increase. Internal energy means simply you can call the strength of our body, or internal energy of our body increases. And the second thing is we do work from this energy. First part is internal energy increase. Internal energy will increase. And second part is work. As we do work in our daily life, so in doing work, some stored energy is used. Okay. So here we can also see that heat cannot completely converted into work. Here our body is taking the 100 joule of energy, but 40 joule of energy is wasted by our body. So heat cannot be completely converted into work. Due to this reason, heat is called disorganized form of energy,
Okay.
or second name is given to the heat is lower grade energy. Lower grade. This is lower grade. Lower grade means its value is less as compared to work transfer. Its value is less.
Okay.
Okay. So now, in thermodynamics, we basically talk about heat and work. As you see that in the therm part is heat, and dynamics part is basically work. So in whole thermodynamics, we only talk about heat and work. Okay. Now, in the thermodynamics part, okay, the energy transfer will be of two types. One is heat, other is work. Energy transfer will be of two types. One is heat and other is work. And our aim to study thermodynamics is to basically convert this low grade energy into high grade energy in an efficient manner. As you see in this heat engine device, for example, let us assume Q1 is 100 joule. Let us assume, okay, and this heat engine is rejecting heat 40 kilojoule to the sink. So this heat engine will deliver work 60 kilojoule. So what is the efficiency of this heat engine? What is
Yes, it's useful over total.
60?
So useful energy. Yeah, 60, yeah.
60%. As we know that efficiency is the ratio of output and input. Here output is 60 kilojoule and input is given to the body 100 joule. Sorry, I have written here kilojoule, not kilojoule, only joule. Okay. So here the efficiency of this heat engine is 60%. Our basic aim to study this subject is to increase the efficiency. We want this 100 joule of energy that is given to the system, that is given to the heat engine, will have to convert into work. Completely. We want this 100 joule of energy as we given to the system, as we given to the heat engine, will have to convert completely in the work. But this does not happen in this device because some heat is wasted. So the efficiency will be less. So the efficiency will be less here. So our aim in this subject is to increase the efficiency of this heat engine. Increase the efficiency so that more heat is converted into work. That means very less. We want very less heat will be rejected. We want this heat very less. This heat is wasted. We want this heat will be of very small magnitude. Okay, so the basic aim of thermodynamics study is to convert disorganized form of energy into organized form of energy in an efficient manner. Okay, when I start the cycle, as Rankine cycle, or Otto cycle or Carnot cycle, then we will learn there that by doing the different approach, we can easily increase the efficiency of engine. So then our main motto is to increase the efficiency of engine. Okay, so in the thermodynamics, we basically study about low grade energy and high grade energy, and to increase the efficiency of the device. So
Okay.
let's move to the next topic. I will dictate to the point. Thermodynamics. Thermodynamics is the study of energy transfer. A study of energy transfer and energy transformation. And energy transformation and its effect on properties. And its effects on properties. Okay. And
yeah,
the aim of, one more point, the aim of thermodynamics study is to convert heat into work in an efficient manner. In an efficient manner. Here the most important word is efficient. We have to convert heat into work efficiently. Okay.
yeah,
Now here two word I have written here. One is energy transfer and other is energy transformation. Thermodynamics is the study of energy transfer and energy transformation. So at first I will tell you about energy transfer, and after that I will tell about energy transformation. Okay. So at first, what is energy transfer? Energy transfer. Okay. There are basically two types of energy transfer. First is heat transfer and second is work transfer.
yeah,
Heat transfer and second is work transfer. Okay. Heat transfer is denoted by capital Q and work transfer is denoted by capital W. In the thermodynamics, whenever you see the word heat, it means heat transfer. It means heat transfer. Wherever uh, it is written the heat, that means heat transfer. Do not confuse with the word as latent heat, heat energy. Do not confuse with this heat transfer. Okay. Now, energy transfer means heat transfer and work transfer. Now, heat transfer. What is heat transfer? Let us assume in your room, it is your room. Okay. In your room, a cup of tea is placed in between the room. Okay. A cup of tea is placed in between the room. Okay. As we noticed that room is at, let us assume room is at temperature of 30 degrees Celsius. Let us assume room is having temperature of 30 degrees Celsius, and this cup of tea will obviously temperature higher than room temperature. Okay. Let us assume this tea has temperature of 1 second.
Yeah, no problem.
Okay. Let us assume this T has temperature. This T has temperature 45 degrees Celsius. Let us assume. So what will happen? What will happen? We have seen after some time T gets cold. T gets cold. Why? Why? Because this T is kept in the room and the room temperature is less. Room temperature is less than T temperature. So due to this temperature difference, heat transfer will occur. The heat of T will go to the room, will go in the room. Okay. So the temperature of T will decrease. But how much? Decrease? Okay. The temperature of this T will decrease, and can the temperature of room increase?
No, it can't increase.
No, because the capacity of this tea cup is very less, is
Right.
very small size, But if I tell you, this is your room, and here a container is placed in the room. A container is placed which is approximately equal to the size of room, and in this container some hot water is placed here. Is placed in this container. Here also the temperature of room is to be assumed as, let us assume 30 degrees Celsius, and the temperature of this hot water is to be assumed as 45. Okay, 45. Now here also, due to this temperature difference, the temperature of this hot water will decrease, because between hot water and room there will be heat transfer. Due to this temperature difference, here the heat of this hot water will go in the room. Now here the room temperature will change, because the size of this container is large. Okay. And my dear, heat is dependent on the size. You have learned that heat is equal to mc delta T. So heat is directly proportional to the mass of the system. That means size of the system. So here the temperature of this room will change. Let us assume here what will happen in the second figure. Here what will happen? The hot water temperature will decrease and room temperature will increase. Let us assume the hot water temperature will decrease to 35 degrees Celsius and room temperature will increase to 35 degrees Celsius. Now the temperature of the temperature of both is same. Can there be heat transfer now?
No, they're both the same.
No, because the temperature of both is same, so there will be no heat transfer. Heat transfer always occurs due to temperature difference. Okay. When temperature is same, there will be no heat transfer. And now this system is called in thermal equilibrium. Thermal equilibrium. Now this is in thermal equilibrium. Thermal equilibrium. Okay. Now let's move to the first example. Let's move to the first example. In this example, the size of, let's move to the first example. In this example, as you see that the size of cup is very small, very less as compared to the room. So here also heat transfer occurs, but the temperature of room, that is 30 degrees Celsius, will not change here. But the temperature of tea, which is at 45 degrees Celsius initially, will be changed. So this temperature of tea will decrease to 30 degrees Celsius, and room is also at 30 degrees Celsius. Now there will be no heat transfer between the tea and room. That means this system is also attained thermal equilibrium. When the temperature of both is same, then there will be no heat transfer. That is, both have attained thermal equilibrium. Okay. So, my dear, what is the conclusion through these two figures? The conclusion part is heat transfer is basically, it occurs due to temperature difference. This is associated with temperature change. Associated with temperature change. Okay. Now what is work transfer? Okay. Let us see. Work transfer is also a type of energy transfer, but the energy transfer which occurs without temperature difference, if the temperature of the two devices is same, but there is an energy transfer between that two devices, then we call work is transferred. That means work transfer is caused due to other reasons of temperature change. Okay. So work transfer is associated with, this does not happen due to temperature change. This happens other than the reasons of temperature change. Okay. If the temperature of two devices is same, there will be no difference in temperature between them, but we see that there is the work transfer between the two devices, that is the energy transfer. Then that energy transfer is called work transfer. Okay. And practical example of this work transfer is in turbine. In turbine, we get the work.